much for having me here. It's an amazing venue, by the way, and amazing conference. So let's start ZisK. Before going a little bit deep in what we are doing in ZisK, I would like to share with you how I see modern blockchains. I mean, how I tend to think about blockchains in the future. Okay? So blockchains, since the last years, we're separating what's the data and what's the execution part. So if we understand blockchains just as data, we can just check. I mean, it's a ledger, it's a public ledger, it's a humanity ledger. If you want, it's a place where you can register logs. I mean, you cannot go back as a ledger, so you just register those things, okay? And this itself, this becomes like a true. You can understand a database that's increasing its data only. And probably that's very much what you need. So on these ledgers, I mean, if you take all this data, for example, in a normal blockchain, these data used to be transactions, and we can do pictures, we can do queries on this data. Okay, so these normal queries, I mean, is we can, and for example, from these queries, we can deduct the state. Or if we take all the Ethereum transactions, we process them deterministically from the beginning, and actually we could calculate, I mean, what's the current balance of my account, or what's the, whatever it's, we know unique things of the state. Okay? There were at the beginning of the blockchains, I remember some chains, I mean, the old people, some of them called, there was one that was called Factom, or something like that, that was very much that. You just put data, and then the way you read this data, the way that you interpret this data, it just needs to be like a consensus, but it's something that's already known. And if we agree in how we read this data, we don't need much more than that. Okay, so these queries, we can actually calculate the queries. The problem of a blockchain like that is that everybody that connects to a blockchain and wants to know the data, they need to synchronize from the beginning, and they need to interpret all this data. Currently, with zero knowledge, we can do those queries much easier. I mean, we can do the query, somebody maybe computes that data, but they can create a proof that a concrete result of this query is correct. And not only that, but I can do queries of queries and queries of queries of queries. We have this recursion. I mean, this tool of, I mean, you're doing a query of a state, you prove the state, and then you create another proof that verifies the query of a query. Okay? So if every time that there is a new block, we just compute the new state, and we can compute the query, then we have this state. Okay? So this is this idea of, we can separate the idea of, we call that dynamic consensus and static consensus. A static consensus is what, okay, we agree, we don't, doesn't change. It's something that's fixed. It's something that the way that we read this data, the way that we query this data, this agreement that we have that this data means this. Okay? And dynamic consensus would be like is the data that in every block is happening. Okay? So we need the blockchain when we want to change this consensus. Okay, so when there is something that changes, we need to reach a new consensus here. Okay? Now forks, well, we need blockchains for forks because it's kind of a dynamic. There is a part that changes, so we need to somehow signal somewhere that this is the new state. Okay? And moving forward to this concept, I mean, we have transactions, but we can have other things. And one example, for example, is linking this with identity. I mean, I can have transactions, but I can have attestations or information, other things that are related, and we can read this data in a specific way. Okay? And all this is possible thanks to this zero knowledge, because we can prove these things. And when we can generate these queries that are complex and we can generate them very fast, this model becomes more useful. Okay? And this is the vision that we are seeing on that. For example, another example is, I mean, we are applying a little bit this concept in EEZ, in Ethereum Economic Zone. But the idea is when you have many rollups that interact with each other, here we are talking only about rollups. So if we just put the transactions of all the rollups in this chain, we can query. I mean, we can deterministically execute those transactions even if they touch different rollups. And of course, we will not have one state. We will have one state per rollup. But the result, the state of each rollup is going to be deterministic. Of course, maybe one transaction is going to touch one of these difference. But the only thing we need in order to do synchronous composability between rollups is just put the transactions there and read them. Okay, so you see how powerful this can be. Of course, this is more complex because we have also layer 1, and of course, this state they can change. But as idea, I think it's interesting to see this. Okay, and finally, well, I want to mention. I don't want to go deep here, but I want to mention that this model also works with privacy. The difference here is that, well, this state is somehow encrypted, and then you need to have a way to encrypt the crypt. Here there are some technologies, but they are not available. I think the next talk is about obfuscation. That's something that is very promising, but using obfuscation, and so you can have all this model, but with privacy in mind. Okay, so why? And then let's talk a little bit about ZisK. Well, ZisK is just a zkVM. It's a zkVM. It's just well, how you create this proof. I mean, how you do these queries. You do these queries means that you need to execute. I mean, you get some data. You need to execute something deterministically, and then you need to generate a proof. Okay, so ZisK it very much helps a lot here. So ZisK is just a program where you can write any program in Rust or in C or any normal language, and you just generate a zero-knowledge proof of this computation. Okay? And it's open source, it's fast, it's secure, it's 128-bit security, it's quantum resistant. The idea is to audit and to formally verify that, and I mean, it scales very well. I would say it's one of the top levels libraries in the current day. Okay? But probably the main property of ZisK is that it was designed with latency in mind. I mean, the idea is to be able to generate these proofs as fast as we can. Of course, also as cheap as we can and with as performance as we can, but the main priority was to do it fast. And in this presentation, I'm going to talk a lot about so all the things that we did in ZisK to make this proof as fast as possible. Because when we want to have information, we want to know fast, and we want to have this information fast. When a block is mined, we want to have a proof of that block as soon as possible. We will see that for many applications, this is important. Of course, this has a lot of other applications, but all of them, they have in common that you need to do them fast. Also mention that ZisK is, it's not a new. It is not a new project, or at least it's not a new team. It's a team that we have been working now about 5 years already in zero knowledge. We built Hermes, we built Polygon, zkVM. We have been running. We are one of the few teams that have been running ZK systems in productions for many times. So, and we have a lot. I mean, we collect a lot of experience in the last years. Okay, so then ZisK is the evolution. I mean, it's the evolution of this team. It's like the cutting edge technology of all the learnings of the last those years. Okay, ZisK is. If you check out the architecture of ZisK, of course, ZisK is a RISC-V VM. Okay, but this RISC-V VM is built on top of a generic ZK system, is the Proofman, and this is all the arithmetization is written in PIL2. It's a specific language for writing arithmetization that allows us to make so all the secure things. I mean, all the arithmetization is compact in a very few lines of code that can be easily audited, and it's very, very specific to that. And on top of that, we have the recursor. That's a package. I mean, it's a framework that allows us to aggregate proofs and to just generate a proof of a proof or a query for another query. This allows you to do it automatically and in a very easy way on top of ZisK. Okay. If we go a little bit deep, what's the core part of ZisK? So the idea is that the important part of ZisK is that when we have a huge query, I mean, I mentioned a program that's quite long, we have a way to divide the problem in many problems. Actually, it's a big proof, and we divide it in sub-proofs or in chunks of proofs. Okay, and then we can do those sub-proofs like in parallel, and then we aggregate those proofs in a big one. Actually, they are not regular proofs because all these proofs are built in parallel in the same transcript. This allows us to connect one each other, but this is what allows us to distribute it. Okay, and we have we separate so we can, for example, have an execution, and we can divide the execution in chunks. Okay, but also we separate that functionally. I mean, we have a specific circuits that are for the RAM, others are for arithmetic operations, for binary operations, for ketchups, for hashes. So we have a very specialized circuits that you can do bunch of operations of a single kind. Okay, and then we join them together in what we call a kind of a bus. Okay, so the idea is that all these circuits, they connect one each other. I mean, from one circuit to the other, they can send like message. Actually, they are not really message. They are things that are assumed in one side that you prove in the other side. So you have in one circuit, for example, in the main machine, that you are assuming that one multiplication is correct, and then you have another circuit that actually is proving multiplications, and you have this bus that says, okay, the multiplication that you assume that was correct here, actually you are proving that's correct in this other circuit. And all these state machines, they connect through this bus, and at the end, we just check that everything is proven. Okay. Well, this allows us to do this bus allows us to do different techniques. I'm going to jump this a little bit, but yeah, this is the core of the bus. Okay, but let's go to the different techniques that we are using in order to make it fast with low latency. That's very much the goal. So the main goal of this project in the last 2 years that we have been working currently. Okay, so when we have a proof, I mean, we generate a proof. Well, actually, we have an execution. Okay, probably in this execution, sometimes we have to prepare that execution. For example, if we want to prove an Ethereum block, well, first there is a preparation. I mean, maybe we want to extract from an Ethereum client. We want to extract all the stateless witness. I mean, it's also all you need to do to prove a block in a stateless manner. Okay, so this would be like a pre-process. Okay, we have the execution itself. I mean, if we want to prove an execution, actually we need to execute. We cannot prove an execution without executing it. Okay, so that's one of the places is executing it. Okay, and this execution, in the case of ZisK, is in RISC-V. So one of the first problems that we have is that, okay, one of the first bottleneck is like, okay, if it's RISC-V, I need to execute code in RISC-V, and I will not be able to prove faster than the time it takes to prove. Currently, the system is mono-thread. There are techniques for doing multi-thread, but the idea is mono-thread, so this gives us a limitation. So the first thing is how we can execute RISC-V code fast. Okay. Once we have this code executed, well, the idea is that we divide this work. So we have a kind of a content plan. The idea is we do a strategy. Okay, we are going to do so many mains, so many binaries. So we are doing a plan of how many proofs, sub-proofs we are going to build. Okay, and then in parallel, we build all those proofs. Okay, these proofs has in general two parts. One is what we call the witness computation. This is a part that's, if you want, is a part that's done in the CPU, and another part that's done in the GPU. That's the more cryptographic, mainly entities and Merkleization of for a start. That's very much what we're using. And once we have all those proof, well, there is a final stage that we need to aggregate them. So we need to join them. So we take two proof and we convert in a single proof. It's a recursive circuit. It's a proof that's proving two proof. So we start with two proof. We have one, and we just do kind of a tree, and we have a final proof. And a lot of times, this is a Stark. If you want to prove it on chain, we may have a last state that it converts to a Stark. I mean, it's a proof. It's a normal Plonk or a normal Gross 16 proof that actually is proving a Stark. Okay, so at the end we have a proof that concentrates everything here. Okay, so what can we do here? Okay, well, one of the techniques that we are doing is, for example, well, in the first two stages, the first thing is, okay, we can do all this preparation. We go to the Ethereum block and so on, and then start the execution, or we can do it a little bit more smart. So the idea is that we can do those things in a pipeline way. So we are preparing, and while we are preparing the proof, we are already start executing that proof. Okay, so this pipelining the inputs. This is one thing, for example, that if we are planning to do latency, we can use this technique. Okay, and here we have like a good reduction for proving blocks in real time. This is an important. Well, this is one of the things that you can do. Another technique that we can do is, well, RISC-V. RISC-V, when you do an execution, we have when you're executing one of those things in a serial way, you have like a lot of pieces of the code that are quite repetitive. Okay, so for example, we call it precompiles. For example, here we can have hashes, or we can have signature verifications, or things that are very concrete and very parallel. Well, one of the things that we can do is, okay, so instead of executing everything in the RISC-V execution, the idea is that we can have a native execution done in Intel that's just doing this. It's like kind of helping the RISC-V execution. So the idea is, okay, you are pre-computing all these, I don't know, these easy recovers or these hashes or these pairings things, okay? And when the RISC-V is having to execute that, it will give him the result already. I mean, it will pre-process. It will help them, because then at the end, this is going to be maybe proven in another precompile, so the RISC-V does not need to execute there, so they can hint them, they can send hints, and so overall, then the execution can go faster. Okay. Another thing to do, if you see here, you see that most of the work in a proving system can be parallelized. We can build this thing in parallel, but there is this execution part that's harder to parallelize. So the idea is that we want to start parallelizing as soon as possible. So we want to have an execution, and we need to split this execution in multiple executions so that we can start using multiprocess as soon as possible. So one of the techniques that we are using, well, first, this execution, one of the things that we are doing is we are transpiling this execution to, so we convert the RISC-V assembly to Intel assembly. The code that we are executing is exactly the same. So, and this can, this transpilation, this allows us to execute RISC-V in around 2 GHz, which is very close to the clock speeds of Intel by there. Okay, so it's a very optimal code. Okay, but we want to parallelize. We want to parallelize that. How we parallelize? Well, the idea is we execute that normally, okay? But what we are doing is we are storing, the idea is that every time that we are doing a read of a memory, we are just creating a lock. Every time that we do a read, we store this lock. So the idea is that then we can execute all these chunks again, but instead of having memory, you have this lock. So when you need to read something from the memory, you get this lock. Writing to memory, I don't care about the memory. I don't have memory. Okay, I already did it the first time. Okay, so this allows us to do a first pass, a first execution of the code, creating this lock, and from there, I can have different chunks, and I can run in multiple processes and running it in parallel. Okay, and from there, I can do the witness computation and the global. So this allows me. So I'm executing. Even when I execute the first chunk, I can already start computing the Windows computation of that chunk. Even while I'm executing the first time, I'm already starting to compute the proofs for this given chunk in parallel. Okay, so from here we go in parallel. Okay, but this works in a single machine. Okay, but the idea is that we can do the idea in multiple servers. So because we want to build that fast, so we want to parallel not in one single server, but in many servers. So the strategy here is that this execution, we are not doing once and then distributing to the servers. We are executing the same thing in all the servers. So all the servers, they know what they're going to do. And then the parallel part, each server, they already know in a deterministic way. They don't even have to communicate which are in this strategy, which piece they are going to have to execute. The first server is going to do maybe the first chunk, the second chunk, and maybe this first chunk of the binaries and whatever. And this is a deterministic distribution. So without communications, all the servers can be done in parallel. Okay? So we can have, this is one of our clusters that we have in Girona. So we can have like many machines working together. All of them, they are doing the execution, but each one is doing each of the pieces. Okay, and maybe one of those is they are finally aggregating all of them. Actually, the aggregation, the technique for aggregation, they don't need to follow a specific pattern on the tree. You can aggregate to prove no matter. The first comes, first aggregate, and you can use different servers. So the aggregation is really fast. Actually, the aggregation circuit is very optimized. It takes less than, I think it's about 85 milliseconds, one single aggregation, and can be done in parallel. So aggregation is very, very optimized in the case of ZisK. Okay? And it's important to see that the interactions between the servers, and if you want what would be a coordinator, are absolutely minimal. Because, I mean, you had the input, you get the input. Of course, you need to broadcast the input to all of them. All of them execute. Each one already knows what they have to execute. There is a couple of interactions, a couple of back and forth. Because, I mean, as I told you, these proofs are built in parallel, so they need to have a single point. It's a single challenge that needs to be broadcast. And then the aggregation part. So we have a lot of proofs at the end, and then all this needs to be aggregated at the end. But the important part here is that the bandwidth between the coordinator and the server is very low. And this allows us, for example, so ZisK is very good if you want to build this proof in a decentralized way. I mean, you can have 3 servers in Asia, another in Europe, another in America, and the latencies will affect minimally in the proof generation. And this is because you don't really need a cluster to build a proof. You need a set of computers coordinated, but minimally coordinated from the network. Okay, so this is one of the important properties of ZisK. Okay, and of course, at the end, we have this Plonk wrapper, which is optional, but if you want to prove this on chain, then this is, we have this piece already done. Currently, it takes less than 2 seconds, and there are some margin here to improve. Proving that on chain is about 250K. It's Plonk, so it's not cross-16. You don't need trusted setup. Well, you need a universal trusted setup, but it's already there, so you don't need to worry about building a ceremony and so on. And it goes relatively fast, and it's 100% available. As I told you before, everything is open source. Okay? And on top of that, we have also the recursor. We are working hard currently on documenting and making it more available, but everything is written already. So the idea is that you can have 2 independent proofs or 3 independent proofs. For example, you have a proof of 2 blocks or 3 blocks, and you can aggregate them in a single block. But it's a different concept. One thing is like inner aggregation. So if we have building a single proof, that's splitted in there. But once you have the proof, you can take another proof and aggregate them. Okay, so you can have 2 real proofs, and then technique is very similar, but you aggregate real proofs, and you can aggregate them using the recursor. Okay. Some benchmarks. Well, you can check it in fproof. For example, there we have some clusters running. but I mean, what's clear is that proving blocks in real time is a fact. Actually, these are the numbers. 97, 96%. This is with, I think this is, Girona cluster is 16 GPUs. In Sevilla, we have 24 GPUs. This can go lower, especially for the clients. Clients are getting better, and there is some margin to improve with the clients. But what's clear is that we are talking about in the order of few seconds to generate a proof. Actually, for easy, for Ethereum Economic Zone, there is one time that's really important. I mean, it's like, so if you are building, we have this composer, this bundle. I mean, we are taking transactions of different chains, and we need to build a kind of a bundle with all these transactions that do all this cross-chain communication. Well, the idea is that while you are building this, you can already start building this proof. And the idea is this time, I mean, so since you finish the bundle until you get the proof available, how long this takes, okay? And this is it's below 3 seconds currently, and there is margin. And this is what allows us to actually to make easy possible this low latency. Because you can only build those proofs when you already have a block, and you have only 12 seconds to do all this. So that's why you need this low latency, and this becomes super important. Okay. Last thing. Well, current state of ZisK is, I mean, it's everything is, I would say, it's finished. We are currently doing some cleanup of the code. We expect to have a version 1.0 the first week, in the next weeks. It's going to be probably a 1.0 beta, because of course here there is a lot of security and things that needs to be run. And also we are working hard on the formal verification. But currently, if you are a user, you would not notice anything from what would be like the final version for at least for ZisK. For the recursor, here there is some work that we are still working, but if you are just doing normal proof, I fully recommend to test it. It's really easy. We simplify it a lot, all the installing and all the user experience for that. Okay? And that's very much what I wanted to explain today. Thank you.